So section 4.7 discussed optimization problems. And this is kind of a really cool section because this is starting to get at some real world type applied problems. Now, we're not actually going to get too much into the real world, but it will give you a taste of how calculus is used outside of a classroom. Now, we're going to start out with kind of a friendly problem. That's the link that I sent you in the chat. What I'd like to do is try and find the value of x at which these two curves are the closest. Now, I'm just talking about the vertical distance between those two curves. And to help out with this illustration, you can do this. You can take the little cursor for B and slide it around and see how it moves that line. What we're trying to do is trying to find where that line is the shortest. Now, the length of that line is given below. You can see it in D. So if I move too far over to the right, then that length is getting pretty long. If I move too far over to the left, again, it's getting pretty long. But somewhere in between, I can get that length to be pretty small. And I don't know, somewhere around here, somewhere around an x coordinate of 0.46 is about the lowest. But that's what we're trying to find, is the exact value of x that makes this distance a minimum. So are we okay on the objective of our problem here? Trying to minimize the distance between those two curves. What value of x does that? Well, this is a nice intro in terms of it's got all the little elements that I'd want from you and the way I teach it in a face-to-face class. So the first thing to do is to draw a picture. So picture. And then with that picture, we want to try and find a function. And that has to be a function of one variable. Now, oftentimes we'll start out with more than one variable, but you got to use parts of the problem to try and rewrite things and get it down to one variable. Next, you want to consider the actual problem and see if there's some interval over which it's defined. You can also kind of think of that as the domain for the problem. So picture, function, interval, and last but not least, in pretty much every problem that you do for me in this class, there should be some calculus. In this case, it's the analysis. So you're going to have to use some calculus. Now for us, that's going to mean a derivative someplace, setting it equals 0, finding a minimum or a maximum, etc. But there's going to be some calculus in these problems. If you're doing this without calculus, you can just mark it wrong right away. There's going to be some calculus involved here. So we got a nice picture from this. Next thing to do is to create a function of one variable. So let's see if we can't do that. Now that function is going to be the vertical distance between these two curves. So I'll call it h of x. So we've got our picture, put a little check mark there. For the function, we'll create h of x is the difference between those two functions. It's going to be f of x minus g of x. Looking back, f of x was x squared plus 1 minus g of x, which is x minus x squared. The only thing that you need to be cautious of is that you put parentheses around that g of x so that that negative distributes itself. So x squared plus 1 minus x plus x squared again gives me 2x squared minus x plus 1. That's my h of x. Okay. Picture, function, interval. Now in this problem, there's no natural limits to our problem. You could try and pick any value of x. Now for purposes of creating this little Desmos demonstration, I limited the values of x to -3 to 3, but that's artificial. I just didn't see that you're going to find a minimum value out past either of these. And it didn't really fit on the screen too well. But there's no natural limitation on the value of x. Maybe somewhere, someplace else, this curve comes back on itself. Who knows? So what I'm saying in kind of a long-winded way is that our domain is -infinity to infinity. There's no natural restrictions on this. There will be on some of our problems. We'll get there. Finally, it comes down to the analysis. I want to find the minimum distance between these two functions. That means I want to figure out where this has a minimum. So how would I do that? Call this my h of x, 2x squared minus x plus 1. Where is that going to have a minimum? Or how could I find a minimum value for this function? This is where we start doing the calculus. What would that mean here?
Set it equal to 0.
There's something we need to do before we set it equal to 0.
Find the derivative.
Find the derivative.
Yeah, thank you. Find the derivative. So h prime of x, I'm not going to bother you with asking you on this one. This one's pretty easy. It's a nice polynomial. H prime of x is 4x minus 1. Set that equal to 0, and we get x is 1/4. One little detail that you have to be careful of sometimes, in fact, probably should do all the time, but we need to make sure that this is actually a minimum. What if that point's a maximum? Could happen, right? So there's two ways you can decide whether or not this is a minimum point. One is the first derivative test, which looks like this. X, f, and f prime. And our point was 1/4. At 1/4, the function has a derivative of 0. But let's look to the left of it. If I put in a value of x to the left of this, like maybe x equals 0, what's the sign of the derivative going to be? And I guess I wrote f instead of h. Probably should have wrote h. There we go. So h and h prime. But to the left of 1/4, what's the sign of the derivative function? If you put in the 0 here, 4 times 0 minus 1.
Negative.
Thank you, AC. It's negative. And to the right, if you pick a value like 1, it's going to be positive. So what's happening with the function? It's decreasing and then increasing. What does that make that point?
Minimum.
Yeah, that has to be a minimum. And actually, it's not even a relative minimum. It's an absolute minimum. Because this is a parabola, it's not going to get any lower than that. There is another way to do this. This is what's called the first derivative test. First derivative test. But there's another clever way to test whether or not something's a minimum point or a maximum point. So if you have a critical point, and you know the concavity of a function, and this is going to be retired. Let me try it again here. So if you have a critical point and you know the concavity of something, you can decide if it's going to be a minimum point or a maximum point. So the second derivative test works this way. If you calculate the second derivative, let's do that. What's the second derivative of h?
4.
If when you put this point into the function, the second derivative is positive there, then you have to have a concave up shape, meaning that that critical point's a minimum. If the second derivative is negative at that point, then you've got a concave down shape, so that critical point is a maximum. Since this is greater than 0, this is going to be a minimum point by the second derivative test. So sometimes it's a little bit more convenient to do one than the other, but it's nice to have both around. Comments on this one. So x equals 1/4, that's our minimum point. That's our answer. We can kind of double check that graphically. If you come back here and actually just type in 0.25 and then look at the value for D, that's about as low as you're going to get it. If you move D around anymore, you slide this around to the left or to the right, the value of D is always going to get bigger. So 0.25 is as small as you're going to get it.
So in step F, when we subtracted the two equations for the parabolas, that we were solving for the equation of the line in between them?
Yeah. So this,
Okay.
this is actually coming up with your function of one variable.
Okay.
At some point, you're going to need a function that you can differentiate so you can find its minimum or maximum depending on the problem. But it's going to rely on this, yes. And that's what we did. We subtracted them because the vertical distance, the distance between the y coordinates, that's the distance between the two functions. Appreciate the question, Cole. Anything else on there, up there on this one? Let's do an easy one to follow this up. And the only thing about this easy one that I don't really like is that it doesn't really lend itself to the picture part of what I said, picture function, interval analysis, that kind of thing. Let's see, it's this one, optimization. Yeah, here we go. Find two numbers whose difference is 58 and whose product is a minimum. Wow, okay. So nothing really, involving a picture here. So we'll skip that picture part and work on the function part. So we want the product of two numbers to be 58. I don't know, let's choose X and Y. Right? And we want the sum to be a minimum. So find two numbers, excuse me. Oh, I got this wrong. I'm sorry, I was thinking of a different problem. Find two numbers whose difference is 58 and whose product is a minimum. All right, so let me try this again. Function, difference is 58 and product is a minimum. X minus Y has to be 58. And the product is a minimum. So I'll call P equals X times Y. Now earlier I was mentioning that in step F, we want to find a function, but we want to find it of one variable. We want this product to be a minimum, but right now it's got two variables in it. So, what can we do to get rid of one of the variables here? Well, we could rewrite this. We could rewrite this as, let's see, let's move the Y to the other side and the 58 to the other side. So kind of change things around. That would give me X minus 58 equals Y. Remember, when something changes sides, it changes signs. That actually helps me out a lot because Now we can replace y here by x minus 58. Sometimes I'll take the moment or initiative to write that this is p of x, just to kind of remind you or signal that this is a function of one variable. Right now, it's a function of two variables. With calculus 1, we can only work with one variable. Later on, if you go higher in math, higher in calculus, you can work with functions of two variables. Not a big deal, but we'll do it with one right now. So that's our picture. Or excuse me, that's our function. Interval. Well, there's no natural restrictions again. There's nothing that says, all right, we can't let x be bigger than this or y be smaller than this, etc. So our interval is negative infinity to infinity. Now it comes down to the analysis. P of x, let's call it x squared minus 58x. I want to minimize that function. How could I minimize that function?
Find the derivative of p of x and then set it equal to 0 and solve.
Yep. Find the derivative, set it equal to 0, solve. So p prime of x is just going to be 2x minus 58 equals 0. I hope you don't mind me fast forwarding to x equals 29. Nice. Now, before you feel all triumphant and think, oh, hey, phew, cool, done with that one. Let's look back at the problem and just check out one detail. We need to find the two numbers whose difference is 58 and whose product is a minimum. I only see one number. How would I get the second number? Any ideas at all?
Can you plug it in for x in the original equation?
Yeah, plug in for x in the original equation. So it's going to be 29 minus 58, which is negative 29. So product is a minimum. I mean, 29 times negative 29, which is what, 831 maybe? 41? Yeah, maybe 841, somewhere around there. In any case, these are your two numbers right here, 29 and negative 29. So, sorry though, no pictures on that one. Again, what I'll be looking for when I look at your exams is steps like these, okay? In particular, I need to see some calculus. Any other thoughts on this one before we move to the next one? All right. Let's move on then. No, I don't want here. This is the one that I want. So here's the problem for you. And let me put the link in the chat in case you can't open them from the PDF. Is anyone having luck opening those from the PDF?
Yeah, I'm able to open all of them.
Yeah.
Okay. All right. Thanks, Cole. But if you're having problems with it, here it is. So we've got a fence. We got 250 feet of fence that we're going to use to enclose a rectangular pasture at the edge of a river. So it's kind of drawn for us here. And let's do what we did with the last one. Let's do the reverse contrast. Ooh, pretty cool. Now, thing is, you don't need any fencing on the side with the river. So let me draw a little picture. Right here. So here's the river. these two sides have the same length, and this one, you know, just can be anything. The question is, how do I adjust these things so I get the most area? If I want the biggest little pasture I can enclose, what would that mean? Now, to see the trade-offs involved here, what you can do is you can use that little slider over here and adjust C. So you can make your pasture really, really wide, but not very deep, or you can make it really, really tall and pretty narrow. Or maybe there's a happy medium somewhere in between. It's hard to tell. I mean, what's the biggest pasture you can get? Now, kind of like the last one, you can judge things, you can get close to the right answer with this little function here. And all I did is I defined the area as being the length of the sides multiplied together. And let's see, how big can I get this? 7,500, 78. So somewhere around here, there's a maximum, but I don't know exactly where it is. So that's where we're going to use the calculus. But hopefully you've got a good idea of what's going on here. There's a trade-off between height and width. Which one gives you the most area? All right, so there's our picture. Now we need a function that we're going to maximize. And that function is going to be the area. How do you find the area of a rectangle?
Length times width.
Length times width. And in this context, with respect to this wonderful artist's sketch, what would length times width be?
X times Y.
X times Y. Awesome. Now, unfortunately, X times Y has two variables in it. I can only deal with one. So, But there is some more information about this problem that we haven't used yet. Let's take a look back at it. That's up here at the top. And that is, we have a total of 250 feet of fencing to use. So how am I going to bring that into the problem? I have to bring it into the problem somehow because I got to eliminate one of these variables. I got to get something that depends just on one variable.
You could write a perimeter function and then solve for one of the variables.
Yeah. So let's see. I've got 250 feet of fencing. Let's not make Cole do all the work. Let's help out. Where do I get that 250 feet of fencing? What takes up all that 250 feet? Or how do I get 250 feet? Based on my picture here.
Both X's and a Y, so like both side lengths and the width length.
Yeah, so X plus Y, or how about 2X plus Y equals 250? Yeah, thank you. So this is another relationship that I can use. From my point of view, it's probably easiest just to rewrite this by moving the 2x to the other side. 250 minus 2x equals y. And that's good news for us right here. Why is it good news for us here?
You can substitute it in the original function.
Awesome. You can substitute in the original function. You can replace y by 250 minus 2x. So our area formula now can be written with one variable. Let me call it a of x, just to kind of celebrate the fact that we're writing this function dependent on one variable. A of x equals x times 250 minus 2x. Beautiful. So picture, function, boy, it's hard to get this function without a good picture. And it doesn't have to be really spectacular. Certainly mine is not. Well, let's think about something else here. The interval. I'll tell you what, it's not going to be negative infinity to infinity on this one. It can't be. You've only got 250 feet worth of fencing. So, that kind of limits things, doesn't it? How does it limit it? Well, let's take a look. If I stretch it all the way out, what's happening? I'm losing all my height and turning it into width. So it's all just kind of in the X direction, nothing in the Y direction. And if I go far enough and wide enough, I'm going to use all the fencing here and none of it for the Y value. And we'll see. Yeah, it's all going to be, no, it's actually going to be the other way. It's going to be all for the Y value and none for the X value. So I can't just use as much fencing as I'd like. Kind of limited. So the most that this could be is going to be 125 feet one way and 125 feet the other way. Nothing left for X. So if I got rid of all the height, then I spent all my fencing in this direction. Let's see. Now, on one extreme, I could put nothing in the Y direction and all of it in the X direction. So that'd be an extreme of 0. On the other hand, let's see. Yeah, so in one direction I could go as much as, or low as 0, and the other direction I can go as high as 125. Now I'm going to put parentheses around both of those. The reason I'm putting parentheses is because if I let X equal 0, basically using all of the fence just to be along the river, then I'm not going to have any area at all, am I? If X is 0, then the area is 0. If X is 125, 125 times 2 is 250, 250 minus 250 is again 0. So these two extremes aren't going to give me a maximum area. I'm going to get 0 area. You can see that if you look at the sliders. Slider here just calculates the area. If I go all the way up to 125, 0 area. If I go down to 0, again, 0 area. Basically, you've just got something that's really, really tall with no width. So that's my interval. Are you okay with the interval? That it's not negative infinity to infinity anymore. A lot of these things have natural constraints on them, like this one. That brings us to the analysis. The analysis isn't too bad because we've got another quadratic polynomial, 250x minus 2x squared. If I differentiate that, a prime of x, that's going to be 250 minus 4x. But I'm not just going to differentiate it. What else do I have to do?
Set
Set
it
it
equals
equal to 0.
Set equals 0. So set equals 0 and solve. I get x equals 250 divided by 4, which is 125 over 2, or 62.5 for x. Okay. How do I know that this is a maximum and not a minimum? How could I tell?
Did you do the first derivative test?
Yeah, you can do the first derivative test. Thank you, David. So let's run through that real quick. X, A prime, 62.5. So here you got a 0. To the left of 62.5, let's pick a number like 1. 250 minus 4, that's going to be positive. And then this is going to be negative. So the function's increasing, then decreasing. That makes this a max. And that's what we wanted. We wanted to maximize that area. So 62.5. Let's plug that in, see if it actually does maximize this area. I'll plug in 62.5 and I get an area of 7812.5. My guess is if I move this around a little bit, I'm not going to find anything quite as big. Yeah, you can get close, but not anything bigger. So that is a maximum. All right. So a little bit better in terms of an applied problem. Comments or thoughts on this one?
Can you just remind me like what the problem was asking us specifically for again?
Sure, not a problem. So it's written at the top here. You've got 250 feet of fence and you want to enclose a pasture and you want to get the biggest area possible. What would be the dimensions of your plot? So I actually should probably do a little bit more here because we have X is 62.5 feet one way. What will be things the other way? So we take that value of X and plug it in here. And what you'll end up with is 62.5 times 2, subtracted from 250. So your X direction is this, and your Y direction is going to be 125. So that's going to be the actual dimensions of your plot. 62.5 feet this way, 125 that way. Yeah, thanks for asking.
Thank you.
Mm-hmm. Okay, so we're going to work with a Norman window in this problem. Norman window puts a semicircle at the top of a rectangle. And the goal of this one is to try and maximize the viewing area, that is, maximize the light coming through that Norman window. Now that light is going to depend on the shape of the Norman window. And for this problem, we've got a total of 30 feet of perimeter to work with. So the distance around this edge, in terms of the semicircle and the base and the sides, has to be no more than 30 feet. So you can play with it. You can see there's some trade-offs. You can have something very tall and narrow, or something very wide and short. But at some point, there's going to be a happy medium. Now, this is towards the extreme side of things. And if I change this up over here, again, you're getting towards an extreme. You can't go all the way down to 0 because that means you have no light coming in at all. It's all height and no width. So somewhere between 0 and 8 something, that's going to be our happy medium. Let's figure out where. Kind of like our other problems. Starts out with a picture, and then a function, an interval. In the book or in WebAssign, they let this whole distance be X. That means the distance from the center of this semicircle to the edge, its radius is going to be X over 2. I'm going to eliminate the need for that fraction by just calling the distance of the radius x. But what we got to be careful is that the whole bottom now has a length of 2x. After you got your circle, or after you got your picture done, we're going to look at the area. The area is going to be formed from two things. You've got the area of a semicircle, which is up top, and the area of a rectangle. Now I just gave this a height of y, just to have something here. So the area of a semicircle is going to be 1/2 the area of a circle, or 1/2 pi r squared. The area of a rectangle is going to be 2x times y. The width of the base times y. So something like this. Now we need to use some information that they gave us about the perimeter, because the perimeter here has to be no more than 30 feet. Thinking back about circumference, circumference is 2 pi r. Then the circumference of a semicircle is going to be half of that, or half of 2 pi r is going to be pi r. So plugging that in, and then all these sides, 2 y's and 2 x's, that has to total up to my 30 feet of perimeter. To get rid of the fact that I've got two variables in my function, I can solve for y from here. I'll move those two terms the other side, divide both sides by 2, and get something like this. That's the equation I can substitute in, or the expression I can substitute in here to get something that just depends on one variable. So what's going to be on one variable? Well, this is going to come down, 2x comes down, and then y is going to get replaced by 15 minus x minus pi over 2 times x, and then I'll distribute the 2x to that term. I'm just substituting this expression circled in pink in for y. If I then distribute the 2x, I end up with 30x minus 2x squared. The 2's here will cancel, leaving me with minus pi x squared. And actually, these are like terms. Let's copy that down on the next page. So that's going to be 1/2 pi x squared plus, let's see, this should be a 30x. Let's do that again. One half pi x squared plus 30x minus 2x squared minus pi x squared, and that's going to equal to a of x. There's like terms in this that you can combine if you'd like. You've got a 1/2 here, 1/2 pi x squared here, and a minus pi x squared there. Those are like terms. So 1/2 minus 1 gives me negative 1/2 pi x squared plus 30x minus 2x squared. And that's what I was looking for, a of x. A of x just depends on one variable. Perfect. Picture function interval. Now, I'm not going to spend too much time getting the most precise interval that I can. Obviously, you don't want to let x go below 0. In fact, you can't even equal 0, otherwise you're not going to have any width to your window. And in as much as we got x this way and x this way, if 2 of those x's were equal to 30, that means x can't be more than 15. And again, if you're at 15, you're running out of material for everything else. In fact, I think probably like somewhere above 7.5 is probably going to be the largest that x could be. Well, we'll just keep a general friendly 15 here. last but not least comes the analysis. So for the analysis, I'm going to differentiate this. That gives me minus pi x plus 30 minus 4x, and I want to set that equal to 0. Let's see, both of these terms are negative and both of them involve an x. So I'm going to move both of these to the right-hand side where they're going to become positive. And I'll get 30 equals 4x plus pi x. If you factor out the x from both sides, excuse me, from both terms there, you can divide both sides by 4 plus pi to get the value of x that maximizes the area or the light coming through that window. Of course, once you get that value of x, you can then plug in and find the value for y. Let me pause here with the value for x, because this has been a long problem. Is there something that I can go over a little bit that maybe I went over a little too quickly that you're not sure about?
I'm a little bit confused about the interval, just on any particular problem, how to find the correct terms.
So we've only got 30 feet of window to work with, and I just took a really simple approach. It's not even the most accurate approach because you've got length around at the top and at the bottom. But just keeping a simple approach, I've got x feet this way and x feet that way. So the width on the bottom is 2x, correct? And if I used everything in just the bottom, then the most that I could have, the widest this could be, would be twice x, 2x. That's not even accounting for the semicircle at the top. So I have somewhere less than 15. I don't want to overcomplicate this and try and find a precise limit on that. I just took kind of a simple approach to say, all right, the most it could be is 15. Reasonably, what I want to assure myself is that I'm not looking for a value of x that's outside of any possible interval of interest. You can't go past 15 because then you'd have 15 feet this way, 15 feet that way. That's your 30 feet right there. So that's how I came up with the 15. You could spend some more time and thought trying to make this a little bit more precise. Like I said, I think the maximum that it really could be is more like 7.5 or 8. But I have to spend some more time on that. I don't want to confuse this issue any further. But did that help a little bit with where I got this?
Yes, thank you.
Okay, good. Anything else on this one? Let's just kind of check that a little bit. If you take 30 divided by 4 plus pi, I think you get about 4.2. Let's see how that 4.2 stacks up. This V of R shows you the area coming through, or the amount of light coming through, which is really just the area. And if I dial it around, getting up to about 4.2, looks like we get up to a height or a value for our light or area at about 63. But when we go past that, it's starting to shrink. So around that 4.2 looks like the sweet spot for the amount of light that we can get in. Once you have the value for x, you can go back and find the value for y through this formula. And it's not going to be pretty, but that's okay. So it's going to be, let me store that number in x. And then I want to do 15 minus x minus pi over 2 times x. 15 minus x minus 0.5 pi times x. Oh, How about that? You get the same thing again. So basically, you get the height of 4.2. And then the bottom is twice that. So it's going to be about 8.4. Because 2 times your x would give you your 8.4. So the base is twice as high as the width. Or excuse me, the width is twice the height. All right, kind of a long one. Any other thoughts or questions? So another example of an optimization problem would be something like this. You've got a parabola, and underneath that parabola, you want to fit a rectangle. The only requirements are that the rectangle touches it, at a couple places. But you can make it really kind of short and wide, or you can make it tall and narrow. But overall, what do you think the goal is going to be? You've seen a couple of these types of problems so far today. What do you think the goal is in deciding for the dimensions of this rectangle?
Find the biggest area of the rectangle.
You got it. Find the maximum area. So, all right. Let me kind of draw some kind of a cheap representation of this, and then we'll get going. And the reason I want to draw something, even though we got that nice little decimals thing, is because we need to label it and work with it. So here, and then nice parabolic shape, like that. Now inside here, we're going to inscribe a rectangle. So let's first run down the axis of symmetry, and then inscribe a rectangle. So up here, and over here, and then finally down here. Picture, yay! Well, let's think a little bit harder on this one. So I probably should write down that this is the parabola 16 minus x squared. That makes these points easy to determine. That's going to be when the y value is 0. 16 minus x squared equals 0 when x equals plus or minus 4. So 4, 0, and negative 4, 0. Now I'm going to kind of stick with what we did with the previous problem. I'm going to label this side x, and this side is going to be y. So x and y. Overall, my goal is to try and maximize the area. So area is going to be area of a rectangle is going to be the length times the width, or maybe the height times the width. And like the last one, because of the way I've done this, I'm going to be a little bit careful with the width. The height, or its length, is y. What's the width here, the way I've defined things?
2x.
2x. Thank you so much. So 2xy is my area. But it's, got a little problem. And the problem is this depends on y and x. I've got 2 variables. I can only deal with one. Suggestions as to how I can eliminate one of those variables. Is there anything that's constraining this? Like maybe it butts up against something. So at this value of x, we're at that value for y. So I'll call this a of x, It's going to be 2x times 16 minus x squared. Or 32x minus 2x cubed would be my a of x. Yay. Picture, function, interval. At least the interval in this one is going to make a lot more sense than maybe some of the other ones. What's the interval that we're going to work with? What's the most that x could be? What's the least that it could be?
Or -4.
Close. X is just this little distance here. So the least that could be, the narrowest it could be would be 0. And what's the most it could be? I think you already said it. What's the biggest that could be?
4.
4. Now, I'm going to put parentheses on either end. And the reason for that is because if we get all the way up to 4, then it's going to be, let's go down this way. We get all the way out to 4, then your rectangle has no height. If you go the other way to 0, then your rectangle has no width. So somewhere in between there has to be a happy medium for this. That is, it's going to give us the rectangle that maximizes that area. Now, I haven't got things quite lined up with my little Desmos demonstration so that it's a perfect thing, but the slider doesn't really reflect X, is what I'm saying. The X that we've got here. It's just giving you an idea of the trade-off. That is, you could have more width or more height or someplace in between, find a happy medium. And we're going to try and find that happy medium. We do that with calculus. I expect to see calculus on your paper. Bonus points if you actually do all 4 parts, picture, function, and interval analysis. That's assuming that a problem requires it. A prime of x is going to be 32 minus 6x squared. I'm going to set that equal to 0. Is that right? Yeah. So the derivative of this is 32 minus 6x squared. Set that equal to 0. We're going to end up with 32 over 6 is going to be the same as 16 over 3 equals x squared. So x equals the square root of this, which I'll write this is square root of 4 over the square root of 3. Now, technically, there's a plus and minus there, but the way I've defined this, x is going to be a positive number. So that's x. How am I going to find y?
Plug it in.
Yeah, plug it in. So if I square that, I get 16 over 3. So writing 16 as 48 over 3 minus 16 over 3 gives me 32 over 3. So that would be its other dimension there. Okay.
Sorry, did you plug it into the original a of x or the a prime of x? Oh, just the y equation.
Yeah.
Okay.
To get y, I plugged it in there, right there, the one that I circled in orange. Anything else on that one? All right. Let's take at least a look at one last one. This one should be on the handout. So the reason I wanted to do this one is because I think that the calculus part of it isn't hard. It's just visualizing and understanding what they're saying might be a little bit hard. So a farmer wants to fence in 6 million square feet in a rectangular field and then divide it in half with a fence parallel to one of the sides. Wow. That's kind of crazy. So what's going on is you've got this rectangular field that's going to enclose 6 million feet. And then you're going to say, oh, you know what? I'm going to divide that in half. So you're going to put that line through there. So if you can get all that out of reading this, then hey, power to you. That's really good. Let y represent the length in feet of one side of a side perpendicular to the dividing fence. So that's going to be the height here. And x represent the length in feet of the side parallel to the dividing fence. So that side. Let f represent the length of fencing in feet. Write an equation that represents f in terms of the variable x. So, wow. There's a lot going on here, but at least we've got a nice picture to begin with. And like I said, it's understanding the picture that's really difficult. So are we good with the picture part? I'm going to do my best to copy that picture down on my paper, and then we'll work on that. All right, so no more regarding the picture. Let me just give my own rendering here. So this total distance is y. And then I've got x, x, x. So what I want to do is I want to create this fence in such a way that it minimizes the amount of area, it's going to be the amount of fencing that I need, while still giving me the area that I require. All right, so let's take a look. So the amount of fencing that I need. Can anyone tell me how much fencing I need in terms of X and Y? Well, I guess there's one subtle thing about this. For one thing, I need X and X and X. I need 3 X's. Plus what else?
1, 1.
It'd be 2y.
Yeah, it's kind of not written, but it's implied that there's another Y over here. So it'll be 2Y. What's the problem with trying to use this? Same kind of problem we run into before. Problem is, it depends on 2 variables. So somehow or another, I've got to eliminate a variable from this. And I can do that by using some of the other information that they gave us. And that is X times Y, the area, X times Y was equal to 6 million feet. So 6 million.
Couldn't you just subtract the 3 and then divide by 2, or no?
Well, but that I can subtract the 3 and divide by 2, but then I get that's equal to F. I don't know how much fencing I need. This is the function that I'm trying to minimize. So that's an unknown, just like both of those are unknowns. So it doesn't quite get me where I want, because you're just replacing one unknown for another. I need to have F in terms of, say, just X. So it'd be 3X plus 2 times. Can anyone think of an expression to use for Y here? What could I replace Y with?
6 million divided by X.
Excellent. If you just take and solve for y right here, it's going to be 6 million divided by x. So 2 times 6 million divided by x. Or in other words, 3x plus 12 million. Yay. That's perfect. That's exactly what I needed, because that's a function of one variable. Beautiful. Analysis. Well, the only constraint here is that I enclose that 6 million feet. So I could do it in a lot of ways. I could do it with a really tall but very narrow corral or whatever this is, or I could do it the other way. It could be very wide and very short. But there's no real natural constraint other than it has to be greater than 0 and less than infinity. You're not going to get any negative solutions here. That should be I, interval. Next comes analysis. Now, as far as the analysis is concerned, I might rewrite this if I were you. This is just my fancy way of writing 12 million. 12 times 10 to the 6. But what's coming up next in the analysis stage? What have we always done at this point?
First derivative.
First derivative. Can anyone see anything that would make this easier to differentiate? Unless you really are a big fan of the quotient rule, then go ahead. I should probably have written this as, let's see, a dot, because it looks like 12x negative, or 10 to the 6. It's really 12 times 10 to the 6 power, which is another way to write 12 million. If I'm going to avoid the quotient rule here, what would I write? Times what? How about x to the negative first? Yeah, thank you. Just x to the negative first. Can you see the advantage of this as opposed to this? Here you have to use a quotient rule. Here, this is just a polynomial type term. It's not really exactly a polynomial type term because it's negative, but you can differentiate it just the same way you would regular polynomial. F of x is 3x plus 12 times 10 to the 6 times x to the negative first. So f prime of x is going to be 3 plus 12 million times x to the negative second. Oh, wait, there's a negative that comes out here, right? All right, so let's just make that negative. We're going to set this equal to 0. It might be worth remembering that this is really an x squared in the denominator. Personally, I'd move this to the other side and get 3 equals 12, 10 to the 6 over x squared. How would you solve it from here? Not a bad idea would be to multiply both sides by x squared and get 3x squared equals 12 million. X squared equals 4 million, dividing both sides by 3. And finally, take the square root. I think it's going to be 2,000, right? This is just scientific notation. In case you're curious, you can enter numbers in scientific notation into your calculator. It's right above the comma, so you have to hit the second button. But if I want to enter 4 million, I can do 4, and then the second button, and then this key, and then a 6. So there's your 4 million. Now I want to take the square root of that, so I'll raise it to the 0.5 power, And there you go. There's your even 2,000. Now, if X is 2,000, then I get Y equals 6 million divided by 2,000, which is 3,000. And both are in units of feet. Awesome. So there's your dimensions, 2,000 and 3,000. Any wrap up on that one? Okay, I think that's a pretty long one for this section, but I think you've got all the tools you need to work through the homework. Good luck with that.